Welcome to the third video on the vectors topic. This one picks up in the magnitude and direction section of the booklet. So here we're going to look at how we find the magnitude of a vector, the direction of it, and then write a vector in what we call magnitude direction form, and also look at unit vectors, i.e. those that have magnitude of 1. So first of all, a bit of notation which you've probably seen before now. It may have first been introduced in the binomial expansion chapter, if not before then, and that's the notation for magnitude, which is basically just putting these two vertical lines alongside a value, and it just means the magnitude, the size of whatever is within those two lines. So in this case, the size of the vector that's between them. Because it's a magnitude of something, we've said in the previous video that magnitude is a scalar. It can never be negative, so the magnitude of something will always be a positive number. So we can write that for vectors in all these different ways. Depends how we're denoting what the vector is, either using the arrow notation, the bold or underlined notation for the vector, ij notation, or column vectors. If we stick those two vertical lines on either side, we're saying what's the magnitude of that vector between them. So it's read as magnitude. Other ways you can read that symbol or that notation is it's the absolute value of it, i.e. that just means get rid of the negatives. There's no negatives. The absolute value of -10 is 10. So that's one way of reading it. The reason it's included here is on the calculators. It appears as ABS above one of the buttons. So you can actually insert it into your calculator. So on the white calculator, it's ABS above the left bracket button. Another word for it is the modulus. So it's called the modulus of it. It has the same meaning, more or less. Or you shorten that and just simply say mod A. So that's the notation for magnitude. And we've seen in previous videos that to find the magnitude, we're just using Pythagoras, whether it's in 2D or 3D. It's just applying Pythagoras. So if we've got the vector xi plus yj, then the magnitude, the length of that vector, is just applying Pythagoras to it. It's the square root of the x component squared plus the y component squared. And similarly for 3D, if your vector is a 3D one with ijk components, then we just apply Pythagoras in 3D. X squared plus y squared plus z squared. So I demonstrated that in an earlier video. It's on page 5 of the booklet. So just a couple of examples here. The one I've drawn, the vector 3i plus 4i. I've used the wrong numbers there. 3i plus 4j. So that's the blue vector. And if we want the length of that vector, it's a 3, 4, 5 triangle. Pythagoras, 3 squared plus 4 squared is 25. Square root 25 is 5. So that vector has length 5. And that's vector A underneath. 3 to the right, 4 up. Pythagoras tells me that the magnitude of A is 5. Second one, the vector BC, here is -4, 9. So the magnitude of BC, which I would write like this, would be the square root of 4 squared. I can ignore the negative since I'm squaring it, plus 9 squared, 16 plus 81, square root 97. Okay, so as we've already seen, Pythagoras is always used to find the lengths of lines and hence the lengths of vectors. Now, in the previous video, we talked about unit vectors, the unit vectors I, j, and k. Unit vectors have a length of 1. I, j, and k are the ones in the x, y, and z direction, respectively. But what if we wanted to find a vector of length 1 in another direction? So for example, on the diagram, I've got the vector A, and I want to produce the vector that's going in the same direction, parallel to it, but the length of it is just 1. That's what we call the unit vector. And the notation for that is just to put this little, it's called a circumflex. We sometimes refer to it just as a hat. So we might refer to that as a hat. So how do I change this vector, which is another 3, 4, 5 one. So the magnitude of that one is 5. It's 3 across. And 4 up. How can I now change that, scale it down so it's got a length of 1? Well, if it's got a length 5, to scale it down so it's got length 1, I'm just going to have to divide it by 5. If I divide the length by 5, I'll get a length of 1. So in that case, I must be dividing the different components by 5 as well. So that must be 3/5. And that must be 4/5. So if you apply Pythagoras on that, you'll end up with the square root of 25 over 25, so I'll get the square root of 1. So we do indeed get a vector of length 1. So this is how we produce a unit vector. The unit vector in the direction of A is A hat. It's the vector A divided by its magnitude. So the one in the diagram was 3i plus 4j. So the unit vector was 1/5 of that, which we could leave like that or expand it like so. So a unit vector, just take the vector itself and divide by its magnitude, because then whatever magnitude the original vector has gets divided by itself and ends up with a magnitude of 1. Examples using all about magnitude and unit vectors. We've got two vectors A and B. First of all, I want to find the magnitude of A. It's a 3, 4, 5 one, so we could go straight to the answer, but I'll show some working. Pythagoras gives an answer of 5. Unit vector, the same one we've just done. It's 1/5 of 3i plus 4j, so 3/5 of I plus 4/5 j. And then we're asked for the exact value of the magnitude of this other vector, the vector that is 2a plus b. So first it'll be useful to have 2a plus b. So that will be, we could go straight to it, but I'll build up to it, 6i plus 8j plus negative 2i, negative 4j. So 6 take 2 and 8 take 4. 4i plus 4j. So now I can say the magnitude of that is the magnitude of this vector. Then apply Pythagoras. So that's root 32 or 4 root 2. I always simplify answers. And I've just put a note there that you must do what I've just done and find the resultant vector. Finding the magnitude of the two bits separately, so the magnitude of 2a plus the magnitude of b won't work, because then you're finding the magnitude of this bit, adding the magnitude of this bit. So if 2a goes in that direction, b goes in that direction, we want that length there. But instead, if we split it up, we're finding that length plus that length, which is clearly going to be much bigger than the one we're asked for. So we must be finding magnitudes of resultant vectors. Next one, we've got magnitude and a unit vector to find. unit vector in the direction of A. So it's building up to it. It's asked us to find the magnitude. Pythagoras first, 3D Pythagoras. So that's square root of 21. So the unit vector, A hat, would have to just be the vector itself divided by its magnitude. In other words, 1 over 21 lots of the original vector. And probably nicer just to leave it like that rather than expanding that bracket and writing each bit over the square root of 21. But we could do if we wanted to. Okay, so that bit was all about magnitude. The next little bit is about direction. Calculating the angle of the direction of a vector. And if we find both of those things, the magnitude and direction, then we're essentially defining it in what's called magnitude direction form. Basically, we state its magnitude and we state its direction. So I've got 4 vectors there. On each one I've just overlaid a coordinate axes. If we're finding the direction of it, then we have to define that direction relative to something. So if I want to say what direction this first one is going in, basically I need an angle and I need to say what that angle is to. So the most obvious and most common one to use will be that one, the angle the vector itself makes with the positive x-axis. So I could find that angle there, call it theta, and state that it's to the positive x-axis, and that would define the direction that that vector is going in. For the one underneath, I'd probably do the same thing. I'd find the angle there and say that it's to the positive x-axis. The one along there, I would probably still find the one to the positive x-axis. I'd probably find that one. But we could find that one instead, as long as we state it's to the negative x-axis. The blue one is to the positive axis. Or we could be asked to find the direction relative to the positive y-axis, and that's for that angle there. As long as we're clear, that would be the positive y-axis. As long as we are clear which one we're finding. For the one underneath, it's heading down to the left. So the angle, just make it clearer by moving that. Oops. I can't move it, never mind. The angle would be there. If I wanted it to the positive x-axis, the one we're most commonly asked for, there, if we're asked for the one to the positive y-axis. As I've written here, very useful, as I've said in previous videos, to draw diagrams if you're not given one already. So first example, find the angle between the vector 4i plus 5j and the positive x-axis. So as I said, most commonly you're asked for the positive x-axis, sometimes the positive y-axis. Sometimes that's referred to as the I direction. I moves to the right, it's the unit vector to the right, so same direction as the positive x-axis. So in other words, it's that angle, the red angle that we're looking for. So I've drawn a diagram, just a rough one, 4i plus 5j. The answer's already there, I was meant to rub that out. There's my positive x-axis. I want to find that angle. Well, I can drop a vertical line down like that, and then I know that this is my 4i, this is my 5j. I've created a right angle triangle, so this is all about trigonometry. If this is my angle, then this is my opposite. This is the adjacent, so I'm going to be using tan. And if it's given in IJ notation, then we're always going to be having horizontals and verticals. So opposites and adjacents will always be involved there. So finding the angle is usually going to be involving tan, unless for some reason we're using the magnitude of it, which would represent the hypotenuse. So, moving back to the question, the angle between that and the positive axis, well, I know that tan theta is opposite over adjacent, 5/4. So theta is the inverse tan of 5/4. Putting that on the calculator gives me 51.3 degrees, rounded to 3 significant figures. Okay, next question. Vector A on the diagram has a magnitude of 10, so I've added that to the diagram. And it makes an angle of 30 with the J. J being the unit vector acting in the y direction, so it's been added to the diagram as 30 degrees to the y-axis. And then we're asked to find A in column vector form. So this vector has been given to us in magnitude direction form. We've got the magnitude, we've got a direction that defines it, and then we can go back now to ij and column vector form. So in order to get it in ij form or column vector form, I need the horizontal component and I need the vertical component. So I've labelled those as P and Q. I've used the triangle at the bottom right here, so I've added the 60 degrees in. So then I'm using this right angle triangle. I could have used the 30. I could have put the P and Q up here and used the 30 instead. But looking at the 60, I know that the Q is the opposite, the P is the adjacent, and the 10 is the hypotenuse. So to find P using the adjacent, I'm going to be using cos, and to find Q on the opposite, I'm going to be using sine. Cos is adjacent of hypotenuse, sine is opposite of hypotenuse. So I'm just going to write those two things down. So I'm using the 60-degree angle, and then P is my adjacent over the hypotenuse. Sine involves the opposites, so that's Q over the hypotenuse of 10. So multiplying both of those by 10, I can say that P is 10 cos 60. Q is 10 sine 60. And I've just added a note there that we call that resolving horizontally and vertically. So I've resolved horizontally to find the horizontal component of the vector, the P, and I've resolved vertically to get the vertical component, the y component of the vector Q. This is really important later in the mechanics chapters we do when we're dealing with forces. We'll be resolving forces into the vertical and horizontal components. So it's something to get quick at, using magnitude, using hypotenuse and direction, magnitude and direction, to quickly produce horizontal and vertical components. Right, 10 cos 60, that's 10 times a half. So that's 5. 10 sine 60 is 10 times root 3 over 2, which is 5 root 3. So this vector A can be written in ij format. So the horizontal component was P, 5i plus 5 root 3 j, or in column vector format, 5 and 5 root 3. Okay, a similar question here. So you could pause the video first and do it for yourselves. I've left the answer at the bottom right there. So resolving horizontally, since P is the adjacent, that would involve cos. So it'd be the hypotenuse, the magnitude of 6, times by cos of the angle. And then vertically, the Q. It's acting down, but for now that doesn't matter. I'm just going to get it as a, I'm just going to get the value of it. Although I could do it as a negative, I suppose. It will be the magnitude, and because it's the opposite, it'll be 6 sine 35, and then put a negative on because it's acting downwards. And then since cos 35 and sine 35 do not give nice surd values, I would just leave it as it is. And that's putting it in ij notation, horizontal with and vertical, with the I and j. Column vector format, well, now that we've got them, we just put them in. Horizontal on top, vertical underneath. Okay, and that's the end of this video. We're going to look at the similar thing but in 3D in the next video.